Today, we've got Dr. Elise Temple and Graham Spinks. Welcome to Accelerating Impact. Very, very happy to have you guys with us. Dr. Temple is a vice president of neuroscience at NIQ Bases. She leads our global commercial neuroscience team. And anytime NIQ does a study that uses neuroscience, a PhD neuroscientist such as Dr. Temple works with the client from the beginning of the project until its completion. She's been with NIQ for 13 years and prior was a professor at Dartmouth and Cornell. Additionally, I'm joined by Graham Spinks, who is a senior research scientist at NIQ. He explores innovative ways to harness AI for transforming complex data into meaningful insights. I wanted maybe if we could start, Graham, with sort of a breakdown of how these artificial intelligence models, we keep hearing about large language models, natural language processing, neural networks, all that sort of jazz, in as approachable a way as possible. Could you sort of help our audience who might not be doctors, such as yourselves, understand what these things sort of look like?
So I think, the way to understand this is that we have an approximation of what the brain does in the sense that at some point came up with the idea, let's create something that looks like an artificial neuron, which is essentially um, just a number, right? And we make some links between all of these artificial neurons and we send information into it and we get information out of it. And if we give it the right type of information and we slowly adjust the weights that are connecting these different links, we'll see at some point that it starts learning to understand what the input is and it'll give an output that is somewhat intelligible. Now, that's the really, really basic origin of neural networks, artificial neural networks. But things have gotten a lot more complicated from there on out. And the latest iteration that everybody knows as ChatGPT or these large language models, they are a more refined version of that.
It already sounds pretty intimidating. So maybe if we start at the beginning of what you said, a neuron is just a number. And Elise, I know sort of you study the brain in depth. Can you give me your take on this idea of neuron as just a number?
At a certain level, that's true even at a neurological level, in the sense that a single neuron integrates information and then comes up with a binary, am I going to pass that on or am I not? And that ends up becoming a single number in essence, like a 1 or a 0. So neurons get input from all different areas through their, dendrites, the things that gather information, and then it sort of sums all that information. And if it reaches a certain threshold, it'll send what's called an action potential to the next neuron in the line, making it go or no go. So it does come down to a very, a nice analogy to the way I understand coding works with binary 0 or 1.
Yeah.
I think the thing that I think is hard to simulate, and why Graham said, we simplistically made a neural network, is that the reality of how many neurons are talking to each other. I don't have the stat off the top of my head, but the number of neurons and especially the number of neuronal connections in the brain is something like, stars in the galaxy or something like that. So that's the part that's hard to simulate, I think, is the complexity of how each of these individual units interacts. There's a famous saying from famous work in neural networks and how memories are formed, which is like, you use it or lose it. What wires together fires together, meaning that net associations that have a lot of repetition end up becoming stronger and stronger. That's how all of these different connections work in our brain, and that's how kids learn, and that's how we learn new things. And any associations, any inputs that are paired, consistently over time become stronger and stronger, and ones that aren't become weaker and weaker. And I think that is the analogy for what Graham described. We often hear about that. The model's only as good as the training set. Same with people and animals. The brain can only take the input that it's given to form these weights or these relative strengths or enduring connections, and what falls away. And so that's why the brain has some of the same problems as these artificial networks. If you have a limited set of experiences, you're going to form generalizations based on those. It's where implicit bias comes from. So neural networks are sensitive to bias if they get trained with a bias set. Humans are subject to bias if we get trained with a bias set, which is all of us are inherently biased because we only are trained on what we've experienced. So in that way, I think it is a helpful analogy to inspire what it takes to think more fully, is have more inputs that are more real life.
I get triggered a lot when people tell me these models are thinking, but we just sort of describe the way that the brain is architected, if you will, and how these models are built and designed and architected. Are these models thinking, Graham?
Well, our current generation, I would definitely say that's not the case. And I think the way for people to understand this is that, what's really happening is we are just giving these models so much data that they're understanding statistical patterns between all of the data that we're handing them, right? So if you give it a lot of examples of how you should connect the dots between one idea to another, it'll be able to, reproduce that for another example, assuming that the example is more or less within the space of what it was trained in, right?
Are they sentient? I associate this notion of thinking with sentience. There has to be a thing there that is doing the thinking, and so there's I would imagine if it's not thinking, it's also not sentient.
This is a whole other issue, right?
Yeah, that's a more complicated issue, because when we're talking about sentience, we're talking about awareness, we're talking about consciousness, and I guess I should let Elise talk more about this too, because you probably know better. But from the perspective of a machine learning engineer, it's very clear that these models don't experience, real life or feelings or anything that we would associate with this kind of sentience or awareness. And I think, one of the very minimal requirements to be able to say I have sentience is that these models would have some kind of model of the world, right? If I do something, how does the world evolve and how does it reflect on me? Because that's essentially what it means to be experiencing the world. And the current models are, you can prove that they kind of have a semblance of notions of how the world works, but you can also very clearly see that they don't understand some of the most common sense things about how the world works. So,
Elise, what's your view on this?
I mean, the funny thing is that there's not a scientific consensus in the neuroscience community about what consciousness even is at a human level, or at a organism level. And so it's very hard to assess if a machine has it, if we can't even agree on what it is from a human level. And there's actually a thing in human development and animal development in certain cases called theory of mind, that at about 3 years old, human children develop an understanding of the idea that their mind is different than your mind, and that the world that they have a mind separate from the world at large. They'll show a 2-year-old like a Band-Aid container, something that doesn't usually have a toy in it, and show them that there's a toy in there, like, oh, this is a secret. And then they'll say, your dad was out of the room. Does he know what's inside this? And a 4-year-old will say, he thinks it's Band-Aids, but there's really a car. He understands that dad's mind is different than my mind, and I know something about the world. But a 2-year-old will say, it's a car. Like they won't understand the difference between your mind and my mind. But to Graham's point, it's been very difficult to code into machines the simplest way of passing these theory of mind tests, understanding that you have knowledge that's different from the world and individuals have different kinds of knowledge that can impact things. So another way that people study this is just look at whether or not things can lie. They have a understanding of deception in that way. It's a similar idea. And
There's actually been some papers recently that have shown
right, that's what I
that,
thought.
yeah, that models appear to be deceptive under certain circumstances when asked certain questions. Um, but I think what we really should remember here is that when we're talking about these things of theory of mind, the theory of mind test for children has been adapted for children. And I
Right,
think when
exactly.
we're talking about these models, a very simple theory of mind test could just be asking the model, who are you? And if the training data that was collected from the wide internet has contrasting information about what is happening while training or so on, in very many cases, maybe the answer is, oh, I'm ChatGPT, but then another model says, oh, I'm the model Llama, which is another model. So just from those answers, you can very clearly see that these models do not understand their role in the world and that they are an entity, like one specific entity different from ourselves. Um, I think that kind of shows that.
Graham, will the models ever get there?
I wouldn't say never personally, but there are people that think that it might be never. And the reason that they think that is because what's happening in the brain appears to be really complex. And so when we talked about, one neuron being a number, well, I think the brain, and correct me if I'm wrong, at least the brain has multiple types of neurons.
There's excitatory, there's inhibitory, and then even that like is more complicated than even how we learned it, because there's different weights of those inputs and different places where they can have a bigger impact. So yeah, this network, a true neural network is incredibly complex, and then it's always changing based on the experiences. Plus, there's some interesting things that I'm not sure are built into the models, but the way biological organisms evolve, there's certain periods in their development where they're especially attuned to certain kinds of connections and making them. So these like sensitive periods or critical periods in development where if you get the right input at that time, then you really solidify these pathways that seem to be hardwired into us to be really important, like vision, but also other things related to puberty. So there's like this additional layer of which things are being used based on the statistical analysis of the world. What has evolution primed us to be predisposed to at different times? And really crucially, how quickly do you get rid of those? It's not just fire together, wire together. It's also use it or lose it. That the losing it seems to be super important. I think this was one thing you wanted to kind of touch on, but it's not just do you forget things? It's that it seems that pruning away non-essential connections is almost as important, if not more, than strengthening used connections. And there's a number of disorders and syndromes in the um, human population that are now considered maybe to be at their heart a problem with not pruning correctly. This is one of the theories of schizophrenia and autism, both are that maybe some of these connections early in development didn't get pruned away. And so this is what leads to some of these symptoms.
That
So
seems
all
pretty.
of that's to say that it's a lot to model.
Yeah, I mean, I I I think the reason I get so triggered by words like the model is thinking or the model is understanding or what does the model understand, et cetera, is because I just view these things as being sort of a tiny fraction
Yeah.
of what humans are capable of doing. For a large language model, it seems like you need to provide as training input the whole of everything humans have ever written. And then it's like, oh, I see some patterns here.
I think that's exactly correct. And so when we talk about how humans learn, essentially the word unsupervised comes up a lot, right? And meaning that, they have all this information coming out. They also extract statistical significance, as Elise pointed out. But on top of that, they are capable of learning concepts on the fly. And these large language models are not. Like, imagine for a second we train large language models on everything on the internet except anything related to physics. And then you would try to talk to it about physics. It just wouldn't have any clue of what to answer in that context because it's just never seen it before. In the end, what's happening with young learners, and I see this with my kids all the time, they basically perform science tests on the world, right? Like, if I push my glass a little bit that way, what happens? It falls off the table, and my parents come and clean it up, and they'll do it 5 more times, and they understand, oh, that's how it works. Now I can manipulate my parents. Um, and if we, would think about, maybe not the next generation, but some next generation of machine learning models, we have them interact with the world. Um, and the idea would be that they learn a better connection between cause and effect, their impact on the world. This related to this idea of a world model, right? So what is happening? Oh, that affects the world model in such a way. So that's a new concept I can use next time. But of course, this is simplifying, right? Because we don't really know how to make an effective artificial neural network that portrays such a world model in an efficient way, such that it can learn new concepts and so on. But there are a
Yeah.
lot of things going on about that, a lot of research going in that
Yeah,
direction.
it's I didn't even, I mean, I assume that there was research in that, but as we were talking, I was having this, I was like thinking, yeah, what is the difference? And, we as primates survive because of our social interaction. So that social relational component is so huge. So we constantly are, doing the statistical analysis on this embodied world and getting feedback all the time, both, the glass fell, but also people yelled, people looked the other way, people came and hugged me. These social cues happen all the time. It is weird the way we don't have neural networks go through this like not perfect phase and then get a lot of feedback and keep growing. That seems like, I'm sure people are studying it, Graham, that seems like an important component of human and animal learning.
I think it illustrates how far we still have to go to really kind of learn in the way humans do, because the passing of time for humans brings all of these cues and all of this information. Whereas for a neural network, is we train everything one time
It's
and that's it.
instantaneous.
And that's it.
Yeah.
There you are. That's
Mm.
your model.
We said we weren't going to get into free will, but this idea of agency,
Mhm.
it sticks out for me because this idea that a child can slide a glass off of a table and over time learn that if I do this, my parents will come running. But to me, that speaks to some sort of level of agency, this idea of integration as well, right? Like you have your conception of the world, you take an action upon that world, you see what happens, and then you integrate that knowledge to say, well, if I want that output, I will go and perform this action again. Do these large language models and machine learning models, Graham, have this sort of characteristic about them?
Not really, not in the sense that you're defining. So definitely not the way we're training these large language models. But um, there's a whole different research line in machine learning, which is called reinforcement learning. Um, and originally, a lot of these, what we would call them agents, the idea was you place them in an artificial environment and you kind of train them to get better at performing tasks, right? And I think this relates a little bit to what you're saying. The question is, how do you best train them to perform the task? And there's been a lot of things tried, and maybe if you reach the end of the level, you get a reward, and otherwise not. And it's a very sparse learning signal, right? It's very hard to understand. I need to do this, this, and that if I want to get to the end of the level. But at some point, some researchers tried, oh, what if we just try to train our agent to maximize the information that they take in, kind of like simplifying what they were trying to do. Kind of, if there is something new, um, go and check it out and see how to interact with it, see what happens. That was the kind of idea behind training. And suddenly, it was a lot easier to train these models to kind of understand what the environment was and how they should navigate it.
Also, we have these incredible reward pathways to reinforce certain things. We get hits of pleasure when we do certain things, and we get intense aversion to other things based on some of these evolutionary ways that our brain was built. So yeah, that's the piece that is not always coded in. Like, what's the reward for the computer, and then how do you hardwire in the the risks that are gonna, put a tamper on that. And then I think with humans, the reason why, whether or not it's true agency, zoo or not, or even animals in general, is then we have individual variability. Like if there's some people that have a certain predisposition to always go after the novel thing, that they're like, their reward is greatest for finding something new. If that's just a little tweak of some genes that randomly get one person a little bit more and another person a little bit less, that can make them respond differently to their exploration of gravity with the glass, in terms of how excited they are about watching the thing break versus maybe negative feedback about people yelling at them if they break the glass. Like, that gives all this variety that can either supply free will or give us the illusion of free will.
I want to ask a related but off the wall question. Graham, was The Terminator a documentary? Will these models be able to sort of have a sense of self over time and say, oh, you know what I would like is more neurons, please, more parameters, please. Let me reprogram myself and make myself more capable and more capable and more capable, and then do away with all these pesky humans around me. I've already sort of taken all of their jobs away from them. I don't really need them anymore.
So I think if we break it down into, will we at some point have artificial neural networks that are self-improving? Well, we're kind of already there in the sense that some of the training data for some of the latest language models are generated by other language models, right? So um, we're definitely going to use AI as tools to make better AI. And the question of, are they going to have their own agency? I think that's the difficult question that nobody knows, because that relates to what is consciousness, what is, how do you even model that? And I think we're still a bit off from that kind of situation. But if you had asked me 10 years ago, would we be seeing a model capable of doing what of ChatGPT is doing right now, I would probably also have said no way. So here we are.
All right, so that's the answer. We don't know. And on that positive note, I would like to thank Dr. Graham Spinks and Dr. Elise Temple for joining us today. This has been an incredibly enriching conversation. I could talk to you guys for hours, and you're a testament to sort of the kind of talent that is all throughout NIQ and all different places. So I feel incredibly privileged to have talked to you guys today. Thank you for joining us in this conversation.